get the results of this flipping algorithm, which apparently seems to be very simple, but it has been observed that it gives really reasonably good result. Okay, so this is these are actually the plots of over an average plot of this ISCAS 89 and ITC 99 benchmark circuits. Now, if you use this zero filling technique, then we see that this with respect to this zero filling pattern set, this reduction in maximum power is about 19%, average maximum power about 19%, average power is slightly more than 20%, etc. Over zero filling, so these are the improvements. Over one filling, so these are the improvements of the algorithm. So you see that there are a lot of scope of improving this even the power value when we are doing this bit flipping. So checking the bit flips. So empty fill improvements are there, but you see for zero fill and empty fill, so these two cases improvements are not that high, because empty fill actually it reduces those scan transitions, and zero fill in most of the cases the logic gates that we have, if we apply a 0, one of the input is 0, the output does not change. So that is why these transitions are less, and the flip flops they normally also have if it is 0, then it is not going to have lot of transitions. So this way this zero fill and empty fill the transitions are less. Of course, this is very much logic family specific, maybe the work that the technology family that has been used in getting these results, so their 0 is consuming less power than 1. For random, of course, there are a lot of improvements that is there. Temperature reduction results, you see that though we have not directly tried to minimize the temperature, but our power minimization was much more focused. Okay, so power minimization was focused for a particular block, it is and its neighboring block, so that we are looking into, and that results in a good amount of temperature reduction. So peak temperature reduction, so this was 5% over zero fill when the pattern set is unordered. So the don't cares are filled, but the ordering of the pattern is not, test pattern ordering is not done. Now this is when the test pattern ordering has been done, that is the combined effect of don't care filling and test vector reordering. So similarly for over one filling, so we have got about 10% and about 15% improvement. So this way we can see that filling plus reordering that can give result in much better power this temperature saving. So temperature variance, so that is also another parameter when we are trying to do this thermal minimization, because if the temperature variation across the chip is not uniform, then different regions of the chip are differently heated, as a result their delays may be different. So the delay faults may create some problem, so they may not be detected properly. So this variance, you see that variance reduction is there. So with respect to the unordered set, so this is the reduction in variance, and when you do an ordering of the test resulting test pattern set as well, apart from don't care filling, then the variance reduces more than 40%. So that is a good saving. So with random filling, you see it reaches more than 90% saving. So that means that chip heating pattern will be very uniform. So this delay faults, missing the delay faults will be that probability is very less. This is a comparison with some previously published work in 2011. So and this is the percentage peak temperature reduction compared to different filling techniques, like so this is output the peak measurement, and this is the reduction part of it. For 3D also, so there are reductions just like 2D. This is the temperature reduction in 3D, this is the variance reduction in 3D. Next we look into the scan chain transformation techniques. So while discussing on this power management techniques, we have seen that there are some approaches for minimizing the scan power by scan flip flop reordering, then true complemented outputs, DT type of flip flops, inserting XOR gates into scan chain, and multiple scan chain based design. So each of them have got effect on the thermal part as well. So using both outputs, so we have seen this example previously, that number of transitions get reduced. Similarly, if you use T and D flip flop, then a flip flop at the time of testing converted to T flip flop, and this also results in good number of transition reduction. So, scan chain modification algorithm. So, what we do? So, this is basically that DT flip flop modification. So, how can we select some of the flip flops to be converted from D to T, so that we can get temperature improvement. So, first we calculate the criticality of the blocks, the maximum criticality C, using the field test set that has got this don't care filling algorithm that has been proposed here, the flip select algorithm, and assuming that all flip flops are D type flip flops. So, that is basically the original circuit where all flip flops are D type flip flop and all scan flip flops are D type flip flops, and the test pattern set is filled using the don't care filling technique that we have just discussed previously, and we calculate the criticality value, the cost function C, which is the maximum criticality value. Now, so now we do these steps. Okay. For every scan cell bit in the scan chain, we convert the cell from D type to T type, or if it was previously T type, we convert it to D type. So, initially all flip flops are D type. So, we take the first cell, convert it into T type. So, as a result, the original test set and their responses will get modified, and this modified test pattern and responses, they will be shifted in and out through this modified scan chain. So, this that way the test pattern set will get modified. Then we calculate the C value and store it in the temp C variable. So, what has happened is, due to this modification, the test pattern that needed to be shifted through the scan chain will get modified, and the response bits that we will get in the scan chain, that will also get modified. So, that the C value that we had computed with respect to the original test pattern set is no more valid. So, we need to recompute it, and that those recomputed values are stored in temp C, and if temp C is better than C, so criticality has improved, then we retain the configuration. Okay. So, this is it is retaining the configuration. So, this particular flip from D to T is accepted, otherwise we go back to the original configuration. So, that the conversion to T flip flop is nullified and it goes back to the D flip flop. Now, this process is again repeated. So, this is repeated for every scan cell bit. Okay. So, if I have got 100 scan cell, then this loop is repeated 100 times. After that, we start the next iteration of this loop. Okay. So, next iteration of this outer loop. Now, again we try to flip the flip flop type. So, previously if this flip flop was converted from D to T, now we try taking it back from T to D, and why this can improve? This can have an improvement because some other flip flops have also changed. So, that may be so with respect to them, it may be better that this flip flop was retained to the D value. So, that way if it is done, then we can we will get back that configuration. So, that is the idea. So, we convert it back from T to D now for maybe. So, this way this another iteration is done. So, if you in two successive iterations, if you find that there is no improvement, that means there is nothing, possibly we cannot get any we cannot do any more hill climbing to get the better result. Okay. So, we stop at this point. Again, this is a very greedy algorithm, but it often gives good result. So, this is actually the percentage reduction in peak temperature. So, these are the various circuits that we have, the ISCAS 89 circuits. With respect to this 0 field test pattern set, so we have got this 10.81 and 10.81% reduction in the in the peak temperature, and sorry. Similarly, this with respect to one field we have got 12.89. So, this shows various improvements, and with respect to ordered field also there are improvements. So, next we look into the internal testing technique. So, internal testing technique means we have got this test pattern generator and this response analyzer inside the chip. So, we have got this basically the BIST type of environment, the built in self test type of environment. So, basic BIST architecture is like this, as we know that this is the circuit under test. So, there is one LFSR. So, LFSR is used as the test pattern generator that is fed to the circuit under test, and then this circuit's output goes to a multiple input signature register MISR. So, that is both time and space compacted, and then this response is analyzed, and when this response is analyzed, so we get the test result whether it is true or not, and this test controller it actually controls all the modules. So, this is the basic BEAST architecture that we have for the testing. Now, this architecture may be modified, and so that we can get some thermal improvement, both power and thermal improvement. So, major approaches that have been proposed in the literature are like this: LFSR tuning. So, we try to tune the LFSR. So, we analyze the impact of LFSR's polynomial and seed selection, and based on that we know that the LFSR will behave differently. As a result, it will generate different set of patterns, and possibly it will have different effect on the this power consumption as well as the thermal situation. Of course, it will also affect fault coverage, that has to be taken. Vector filtering we have seen previously, that is test pattern generator which do not detect any new faults, so that are excluded from the test pattern set. So, that can also be used, and this low power test pattern generation. So, we feed highly correlated test stimulus bits among non adjacent scan cells, among adjacent scan cells every scan chain. So, this is another possibility, that is if two successive bits are very much similar to each other, then it can generate a low power test sequence. So, this is also done, but they do not contribute to the overall peak temperature reduction and thermal variance reduction. So, another architecture which is known as LT-RTPG. So, this is a test pattern scan based test per scan based test pattern generator for low switching activity. So, this tries to minimize the switching activity. So, what is done? This LFSR, a number of inputs of them. So, they are inputted to a k input AND gate, and this k input AND gate. So, this is actually it is fed to the T flip flop. So, whenever all these inputs are 1, whenever all these LFSR inputs are 1, then only this T bit will be 1. As a result, this input that we are feeding to the scan chain, so that is going to change. So, ideally we should take say the LSB of LFSR and connect it serially to the scan chain. So, whenever this LSB switches, so a scan transition is introduced, and that is taken as the new that when a number of bits have been shifted into the scan chain. So, that is the test pattern. Now, as soon as you make it a k input AND gate, that is controlling the this T flip flop. So, possibility of introducing a transition becomes much less. So, that way this scan chain it will have very less number of changes, very less number of toggling in its input. So, that as a result this the pattern that we are feeding to the circuit. So, this is basically going to be less. So, for the primary inputs, so there may be a test pattern generator which feeds the primary input part, but for the scan chain part, so these transitions are less in the scan chain. So, this test pattern generator, so it may be working in such a fashion that it uses this test patterns the primary input part of the test pattern very judiciously, and so that it does not have to depend much on the scan chain inputs, but scan chain inputs are mostly kept similar. So, that is the way this circuit operates, the LT-RTPG architecture works. So, if we want to use this for temperature minimization, so first of all we determine critical parameters that are responsible for variation of temperature. So, first we need to know like what are the parameters that are going to affect the temperature variation in the circuit. Then we optimize using critical parameters. Okay, so, we optimize using the critical parameters, like after this study we will know what are the parameters to be optimized, and based on that we do perform an optimization based on critical parameters. Then this test pattern generation will be done using the parameters specified by the solution. So, this solution will tell us what are the typical critical settings for the LFSR, and based on that we can do these things. Now, once we have done this test pattern generation, we can do a thermal simulation using say the tool hotspot or similar such thermal simulation tool to get the temperature profile of the resulting situation. So, the initial experimentation that has been done, so that has we do many things like vary polynomial with seed and tapped stages unchanged. Like if you have an LFSR, so LFSR there are various issues like so what is, so if this is the LFSR, then the one thing is the polynomial. What is the polynomial that we are using for feeding back to the first cell? So there is an XOR gate, and this XOR gate actually feeds back the first cell, and what are the cell positions that you are tapping in? So this will definitely come, and it may be that we tap out these two positions and take them into this LFSR. So that will tell us what is the characteristic polynomial. So if the characteristic polynomial is changed, then it will behave differently, so it will generate different set of patterns. Second important thing is the varying the seed pattern. So particularly if the LFSR is of maximum length, then varying the seed pattern, it will generate patterns in different parts of the of its state space. So as a result, the patterns generated will be different. So this goes through a number of cycles, maximum length LFSR. So it will go through a number of all the 2 power n minus 1 states in the in its state transition, excepting all 0. So if you start here and run for 1000 cycles, you will get some set of patterns. Okay. If you start at this point and run for 1000 cycles, you will get this set of patterns. Okay. So all these patterns will be generated. So that way, depending upon the seed value also, the sequence generated will vary. As a result, the fault coverage, power consumption, temperature, everything will change. So that is another parameter. Third parameter that we are looking for is, so there the way we did it is that this was feeding one AND gate, and this AND gate we were tapped from some places, maybe these 3 places we tap, and then it was fed to the T flip flop in the LT-RTPG scheme. So this was fed to the T flip flop. Now from which positions we are tapping, so that is also having an effect. So we just try to see which effect is more critical. Okay. Like if we do an analysis like this S5378 circuit, we run with different we run it several times by varying the polynomial with other 2 factors remaining same, the tapped seed position and this the seed and the tapped stages. So they remain keeping them unmodified. So we just vary the polynomial of the LFSR and see what is the maximum temperature and minimum temperature that is achieved for this particular circuit. So you see there is a variation about 4 degree. Similarly, if you vary the seed with polynomial and tapped stages unchanged, so this gives rise to a variation of 15 degrees. And if you change this change the tapped positions feeding the AND gate, and the polynomial and the seed they are kept unchanged, so this gives a variation of 4 degrees. So this in general, so this so for example for the B21 circuit, so this gives a variation of 5 degree, this gives a variation of 3 degree, this gives a variation of 4 degree. So though it apparently seems that 2 degree, 3 degree, 4 degree saving, so how great it is, but it is also useful because you see it is a question of the chip getting damaged and all that. So it is better that we even if the value is saving is not that high in temperature, maybe if we run it for a longer time, the temperature will build up, and that way it is going to be destructive. So you see that there is no clear cut distinction between which one is more important. So possibly we have to optimize all of them to get a good temperature aware method. So these all the 3 they turned out to be critical parameters: the primitive polynomial used by the LFSR, the initial seed that we feed to the LFSR, and the tapped stages of the LFSR. So all of them become critical. So when all of them become critical, so how to work? So again we use a particle swarm optimization based formulation. So in this case, I have got if I have got this say the LFSR primary, if the LFSR is of n bit size, then the first n bits of the particle it represents the polynomial. So if this bit is 0, that means the position is not used in the feedback function. If the bit is 1, that means the position is used in the feedback function. So that way, since one characteristic polynomial will tell us what will be the connection pattern of the LFSR. So these are the various first n bits that will tell us what is the connection pattern. Next part, next I need to tell what is the initial seed, and again there are n bits. So this n bit values can be fed here. So, this is the initial seed value. So, the initial seed value will be having the proper one. So, this will be having this with which value the LFSR will start functioning. And then what are the tapped stages? Tapped stages feeding the AND gate. Again, if it is an n bit LFSR, so I need n positions here. So, the bit being 0 will mean that the position is not connected to the AND gate, bit being 1 means that position is connected to the AND gate. So, by this structure, by this particle, we can represent a complete solution. The characteristic polynomial that is chosen for the LFSR, the initial seed value and the tapped stages that are there. So, all of them can be utilized, all of them can be specified. So, initially the particles are generated randomly for the first generation. So, they are generated randomly. So, that is then this every bit of the part. So, then this the fitness has to be evaluated. So, fitness is same as the X filling work, that is the criticality value C that we have used. So, that criticality value can be utilized, and then based on that this formulation evolves, okay, and then whatever comes as the final solution. So, we can after a number of generations that we have run, so we can see what is the best solution that is produced. So, if we do that way, so this peak temperature variation, fault coverage and etcetera. So, if we look into those parameter in a normal BEAST scheme where there is no such choice of this polynomial and seed and all that. So, we see that this 5378 circuit. So, this original temperature of 432.14 degree Kelvin, fault coverage was 97.32. Now, if you use this PSO based LT-RTPG scheme that we have just discussed, so peak temperature reduces to 360.30 degree and fault coverage also gets reduced. Peak temperature reduction is 16.62% and this thermal variance reduction is 92.38%. So, you see that there is a huge improvement in the thermal variation, there is also considerable improvement in the peak temperature part. Of course, fault coverage reduces because of the thing that the emphasis is more on this criticality factor, which tries to minimize the temperature part rather than the fault coverage part. So, fault coverage gets suffered. So, this can be handled, this can be taken care of by taking help of this running the PSO further for more number of generation, or making the test making the LFSR to run for more number of cycles. Actually, these results are obtained by running the LFSR for 1000 cycles. So, if we run it for more number of cycles, then more patterns will be generated and the fault coverage value will improve. Okay. So, this will be and the peak temperature values will worse. So, this will become slightly worse than what we have got here, but still we can get saving in the peak temperature, may not be say as high as this one, but at least 10 to 12% improvements can be obtained, and the fault coverage value can be restored to the original values. Okay. So, that way this BEAST approach. So, we can choose this polynomial, we can choose this seed, and we can choose the tapping positions and use LT-RTPG type of scheme for reducing the thermal variation and peak temperature.